Welcome to Spring LIB.
7.57, so we have a mass on a spring, so we stretch it to some distance x before releasing it, and so the spring compresses itself again, pulling the mass along with it, and so we want to find what the speed of the mass is when it returns to the equilibrium length of the spring, and when it is halfway between where it started and the equilibrium length of the spring. Unfortunately, here we're calling both the coordinate x and also the initial displacement x. So this is when the coordinate is 0, and this is when the displacement is, or when the coordinate is half of the original displacement. So this setup here is a little bit unfortunate, but as long as we're careful with that, we can get by without too much trouble. So the work that was done on the spring while it's being stretched, is equal to the work that the spring does on the block to bring it back when it's compressing, and that's going to be the change in kinetic energy of the block. So if we're releasing it from rest, then its change in kinetic energy is 1/2 mv final squared minus 0, the initial kinetic energy, and this has to be equal to the energy that was stored in the spring, so 1/2 kx squared. We don't know what k is, but we know what F is, because k is the force required to move it to x divided by x. So in this case, the final speed is the square root of fx over m. Now we want the work going from x over 2 to x, or vice versa, depending on whether you're talking about stretching the spring or the spring pulling on the mass. In both cases, they're the same. So that work is going to be x over 2 to x of f dx. And again, this is a little bit unfortunate that we're calling these x's are constants, but then the x in the integral is a variable. So this works out to be 3/8 kx squared, where x here is the constant x. And so we have 1/2 mv final squared will be 3/8 kx squared. And so using f over x again for k, we get that the final speed is 3fx over 4m, with the square root of that.